I have made now a sample project that has no robot code or anything in it, right? It's just the robot.java file that comes standard. So now what I've done is taken out all of the useless code that they put in from the default, right? And we don't need any of these imports, so we can get rid of that too. One other thing that I've done that I don't really want to go into too much because I don't really want to encourage this, but I do it, so it's fine, is I've overridden the default robot class that this package used, because I prefer to program everything using the sample robot program, because it gives you basically nothing from the WPI library. Like there's nothing to help you with managing the robot transitions. So if you use this, you have to be very careful with it. But the reason I've overridden the robot class that it generates, the base class, is because the method, the whole class itself is deprecated. Like they just say don't use it, and I tell them no. So I've now made my own robot base class, and the only change that I made was I removed the tag that says deprecated. So now I don't get any more warnings, and I'm happy. So we have here 4 main methods, right? Robot init, autonomous, operator control, and test. There is also a disabled method that we can override. So what these are the methods that the robot will run when it reaches each of these states. Now, an important thing to note is that because we're using the sample robot class here, these methods execute once only. I mean, they will loop in the superclass continually, but generally what I do is I'll put a loop at the bottom of every method that continually checks while we're in that mode. That way we can control the timing, and the WPI library does not control the timing for us. And I'll give you an example here. So we would say while is autonomous, we'll just sleep. And it's complaining because we need a try catch, right? Because the thread can throw an exception. So what this is going to do is this is the code that's going to be executed continuously while we're in autonomous inside the while loop, right? And I've now set my loop rate to 100 milliseconds. Well, we talked a little bit before that 20 milliseconds is too slow. So why did I set this to 100 milliseconds? And the reason is we're not really going to use this. This is just where we instantiate some of the variables that we're going to use later, and then we're going to spawn a new thread to do the other processing that we need to do. So, like I said, we're going to use CheesyPoof's 2017 library. So let's pull their source. So inside their source code, we want to find what they use to do their tasking, right? For lack of a better term right now. They have this class called looper. And the looper is basically going to do exactly what it says, right? It's going to be running continually in a loop all of these different things. And the way it works is we can register things into the looper. We can see right here where they register their enabled loops. Okay, now with this task manager, we can control the refresh rate, which is another thing that this is something that we talked about. It's what we want. So let's import the looper. Now, one thing that I am going to do to help simplify things is in the Cheesy Poofs code, they have their classes spread out in a lot of different folders because they used it all internally for themselves. They didn't make it so that it could be easily dropped into another library, right? We had to go through and gather all the source files into one area in order for everything to work. So instead, what I'm going to do is I'm going to start by using our 2018 code, which we've converted the library to be a little bit more user-friendly for quickly changing from one robot to the other. So under utilities in our source code, we have this folder called trajectory following motion. And inside this is the majority of the classes required to implement this implementation of path following. So let's take this entire folder and copy it into our project. So let's make our utilities folder and paste the trajectory following motion. So we see that popped up here. Awesome. So like I said, this is almost everything that we need to implement what we want to do. But we have a couple errors here. This is just a referencing error. So we're missing a constants file, right? And generally, when we do this kind of implementation, it's helpful to make a constants file due to the fact that all of your constants and values that can be changed are all in one place. So if you're doing tuning, the constants having everything in one place is usually beneficial to you. So let's make a constants file. Create class constants. I don't know if I can do that in a new file. Let's try it. Right here. Utilities, create class constants. I don't see it yet. Here, it's here. Okay. So, inside the constants, right, let's look at what we've done for constants, right? There's going to be some specific constants that we need to import in order to do our path following properly. So this is the utilities constants file from our robot 2018 repository. So under robot physical constants, we need to import the geometry, right? We need to import the profile for our wheels and our drive base. So we're going to take all of these constants and move them into the constants. So what's this path adapter that we have here? Well, we created a system that was different than the Cheesy Poof system, because the game was a little different this year, of adapting paths, because field dimensions are not always the same, right? So we created a way to automatically adapt the paths to the real field measurements based on a profile that we would create, and then it would apply transforms to it. We're not going to cover that today, just due to the fact that it's a little bit more complicated, and I really just want to focus on the basic path following implementation. But if we have time at the end, we can talk about the implementation of it. So instead of having this dynamic wheel diameter from the path adapter, we're just going to use our constant, which is 4.875. Now, we also need to grab some of the path following constants, which are down here. Path following constants. We're just going to take this whole section and copy it into our constants. And we'll cover which values need to be adjusted a little bit later. Okay. So now let's grab the looper, right? We have a folder called loops that contains our looper. And this is basically the task manager that we talked about before. Now we have an interface called the loop, and now we're going to leverage polymorphism to implement subsystems as loops. That way we can run periodic tasks through our looper synchronously. So let's take the whole loops folder and move that also into our utilities. So now we've got loops. Utilities, loops, the looper. So we're missing a couple constants again, right? So let's grab the constants. K looper dt. Doesn't want to find it. So one of the things that we've done as an extension to what the Cheesy Poofs have done is create thread priorities, so that we prioritize our threads just because we have a lot of different threads that are spawned to manage a bunch of different tasks. That's really not that important for a base implementation here. It's just something to note because it is one of the constants we're missing. So let's also grab this block here, right? We want to just import a couple constants that will help us with unit conversion from the talon. Remember how we talked about the formulas for calculating the feed forward gain? We had 100 milliseconds per minute, and we had sensor units per rotation. So while we're in here, we'll grab those constants. Those will come later. And then we grab the looper dt, which is the desired time delta on the loop. Currently set to 5 milliseconds. We may not achieve that because that's a pretty fast loop. But we'll do our best. Okay. So now we've got our looper. Now, this is a very important class. What we have here is the robot state estimator. This class is the class that generates the odometry that we were talking about, that actually tracks the robot's position. This is probably the most important section of the path following in order to keep your robot very accurate, right? So you'll see that we have this class here that's red. We need to implement a drivebase subsystem. that controls the drive base, right? So let's do that. Let's see where it is. Okay, it's under robot. We need a package for subsystems. Let's make a new package. And now we'll make a new Java class, drivebase subsystem. Okay. So another important thing to note is that for all of our classes that we create, the majority of them, not for anything big, we instantiate them as singletons. Now, what is a singleton? What does that mean? Well, when a class is a singleton, it means that there can only be one instance of it. So the way that we do that is we create a private static instance of itself. And then we make a static method that instantiates the static instance of that class. And then anytime we want to use that class, we return the static instance of it. So we're still allowed to use instance data in our class because it's not fully static, but we only have a static instance of it. So we don't have to keep track of a bunch of different objects that are all different instantiations of the same thing. We only have one. So now this will just check if instance is null, instance equal new drivebase subsystem, and then we return instance. And then what we do is we make the constructor of this class private so that no one else can call it. So if you try to instantiate, if you try to directly instantiate an instance of this class, it will give you an error message because the constructor is not available. You have to call the getInstance method on the class. Okay, so it looks here like we have a few methods that we want to stub out real quick. We want to get the left distance in inches and get the right distance in inches, right? And these look like they're going to be doubles. So let's make Okay, now we also need to get the gyro angle. And the left and the right velocity, notice, in inches per second. Okay, so that's another unit thing that we're going to have to worry about later on. Okay, so now we have all of the methods, I believe. Okay. So in their library, the gyro angle is not a double. It's actually a rotation 2D, which is basically just a wrapper class that they have for an angle. So you can see here the rotation 2D class. It just is a way, it's another way to represent a rotation. Okay. So let's see. Next, we need to get the talons in the code. Like we don't have any of our drive-based talons instantiated, connected, or programmed yet, right? We need to tune the control loops on the talons. We need to set the control IDs, the gains, everything. Everything needs to be connected. So because this robot has already been used so much, I am going to take some code just to save time, but I will explain it as we go. So what we do is we have a controllers class where everything that we use for controllers is instantiated and connected. So the base motor controller class is what we use to control our slaves, because it's we wrote the code so that you could sub in other devices besides the Talon SRX, because there was a period when we were looking at using the Victor SPX. So we made the code polymorphic in order to be able to choose between those two motor controllers for slaves, but we ended up settling on Talon SRXs due to the available current monitoring portion of it. And now what we have done is written a driver, which is a wrapper for the Talon SRX. So let's make a drivers folder. So I'm just going to comment out some of this reporting here. Okay, so now what this does as a wrapper extends the available number of gain slots in the PID. You don't need it for this. This is just a wrapper that we've written for convenience, for usage, for other stuff. But it does make some things more convenient just because of the way we've written it. So now you see this constant K timeout MS. In the new Talon library, they have implemented error codes for almost every function that you can perform on the Talon. Now, sometimes on the CAN bus, when you're sending frames very quickly, acknowledgements get missed and updates get missed. Sometimes stuff just doesn't always work the way you want it to. So we've written code that does error checking on set operations as we go along when we're configuring the Talon, when we're setting gains, when we're doing things like that. Then we check the error code. If the library received an acknowledgement from the Talon that the set was successful, then we continue on, right? But if we get to the end of our block and any one of our sets failed, we then just have a retry loop that will retry a maximum of this constant that we set for retry counts. And the timeout is how long it waits for the acknowledgement back from the Talon before it moves on and says it failed. So let's grab those two constants from our constants file. Where's constants? So the reason we have a fast implementation of that is that when we're in the middle of our code and we have to do a retransmit or an update on something, we don't want to wait for 20 milliseconds because it's too long, so we changed it to 10 milliseconds. But we don't always want to do that because sometimes you miss acknowledgements. And then the retry count is that if anything fails, we'll retry it 3 times. This action timeout we won't need, I don't believe. Okay, so now let's import our Talon SRX. So what are we missing? Well, we're missing our controllers get instance, which is also going to be a singleton. So let's make a private static controllers. That's not what I want. So you can also do this like that. I'm really not a fan of that, just for the simple reason that if you ever do make a subsystem where you need error handling, you can't do any error handling like this. So I prefer to instantiate it to null and then make a get instance where we can do error handling. We don't need that. Okay, so this whole method we'll just get rid of. You don't need to know the PDP current. It's just not important. What are we still missing? This error message. Okay. Questions so far? Any questions as to why we do some of the things we do them the way we do? Okay. So now we continue on. Now, in our drivebase subsystem, we have to instantiate the talons, right? So this depends on how many talons you have in your drivebase. For our drivebase, we have 6 sims, right? So we're going to have a master on the left, a master on the right, and then 2 slaves on each side. So we can import those here, right? So we have a left master, right master, left slave 1, left slave 2, right slave 1, right slave 2. Now, remember how we talked about setting up the encoders to make sure that the motors and the sensors are in phase? Well, since we talked about that already, I'm going to save time and input the configuration for our robot, right? So, first off, we have to get them from controllers. So let's import controllers and now assign every one of our objects that we have that we've made as our instance data to the actual talons themselves. So inside controllers, we're going to make a few methods here, right? So in the constructor, we have to say right, we have to put in our device ID. What is this asking me for? What do you want? Ah, okay, the PDP channel. So the wrapper class also accepts the PDP channel as an input so you can compare the current to the talon to make sure everything's working, but we don't really need it, so we're just going to put in arbitrary values. So because our electrical team likes to move things around so much all the time, we've assigned the IDs to constants in our constants file so that we can change things very quickly, if I can find them. So here is our drivetrain. It's bad practice to assign any Talon SRX or any device other than the PDP and the PCM to device ID 0. Oh my God. Okay, we're good. it's bad practice to assign any motor controller to device ID 0. Because when you put a new Talon SRX on the robot, its default ID is 0. So if you have another device that has that ID, there's going to be a conflict, and you're going to have an issue configuring it to the right ID. You lost me? All right, let me rework some things here. How's that? Okay. Okay. So, you remember how I was talking about changing the frame rates on all those devices earlier? Well, we've made a class that does that for us. So when we create a new Talon, we have a class that has a method that builds our device for us with parameters that we've input. So let's take a look at that class. If I can find it. Let's see, it should be under utilities, drivers, CAN speed controller builder. Let's copy that over. Okay, let's take a look at this class. So we have a lot of error reporting built in that I'm just not going to cover. Because really, how you log errors is really up to you, but it's helpful sometimes. So we change our control frame, our status frame general, and our status frame feedback periods. On master Talons, we increase the rate to 5 milliseconds. And on slave Talons, we decrease the rate of the general and the feedback frame to 100 milliseconds, and we leave the control frame at the default value of 10 milliseconds. So now instead of directly assigning these to new devices in our controllers file, let's use the speed controller builder so that we have the advantages that we talked about. And of course, our PDP channels are constants as well, because they keep moving around. Okay, so now our controllers is happy. When you're creating a slave Talon, it takes in one more argument, which is the master Talon, right? So it will make the slave follow the master if you put that in our speed controller builder here. Okay, now we need methods on controllers to get our data. All right. So far, so good. Now that we've actually gotten our device, we can set the sensor phase, we can set everything correct. Now, inside of our drivebase subsystem, we want to make our loop, right? We want to make the thing that's actually going to run continuously. And the way we do that is to take this here loop and put it there. Now let's take a look at what is actually inside the loop, right? So the loop is the interface that we have taken. So we've extended the library that the Cheesy Poofs made to have an on first start condition inside the loop. So the very first time that loop is ever run, that's like an initialization condition that you can do the very first time the loop is run. And then there's an on start, so this method will run every time the looper is started. And then this is an on loop, which will run as the loop, right? This is the periodic method that all of our data and all of our things are going to be put into that's going to continually run. And then there's an on stop method that's going to run when we stop. So we have a subsystem home method for on first start, right? So basically, what we want to do is we want to reset our gyro and zero our encoders, right? We want to make sure that we're starting from 0 when we start. So let's take a look at this. So we haven't created our gyro yet, but let's take the subsystem home method, right? We're going to zero the navx as the first step. Then we're going to zero our encoders on the left and the right side. And this is one of those instances when we're going to use the fast timeout because we're running in actual code. One of the things that the Cheesy Poofs did differently this year was that in disabled mode, they were periodically zeroing their encoders. So anytime the robot was not enabled, it was constantly re-zeroing itself, which was a good idea. I haven't switched to that yet just because I'm a little worried that it could switch to enabled in the middle of zeroing something. I'm not really sure. I'd have to look into that more before I do it. But to be fair, if they do it, it probably works pretty well. So now we want to make our gyro, right? Because now we need our sensor, our gyro, in order to get data from it for the heading. So like I was talking about before, we've created a wrapper for the gyro called the navx. All right, we don't need these things. So we had at one point put in a method to detect tipping and collisions. It never worked with any degree of accuracy. So for this demo, I'm just taking it out. Like, it's useless. So one of the reasons why we need a wrapper for the gyro is that we need to invert the coordinate system on it, because on the gyro, counterclockwise is negative. On the navx gyro, counterclockwise is negative, I believe. which is not how physics works, right? If from you guys who remember the right-hand rule, right? Counterclockwise is positive. So we invert the coordinate system using a built-in callback. There are other ways to do it, but this is what the cheesy poofs did, and it works well. You can add things into the callback if you want. There are some things in the callback that aren't used, but we just took the raw class and used it, right? And one thing to note that's important is that their getYaw method returns a rotation 2D, which is that transform that we were talking about before that's not a raw degree value. Another good reason for the wrapper. So now in our controllers, we need the navx. So let's bring it over. Import it. Instantiate it. And we instantiate with a try catch because there was some error that was being thrown for something, but it's really not important. All right, and if you're using the navx, you want to use the SPI port on the MXP. Inside of our wrapper class, we automatically have it set to request the maximum refresh rate of 200 Hertz. So our maximum update rate is already selected inside of our wrapper. Now we just need a method to return the navx, right? We'll just call it getNavx and bring it right over. So here we need the same thing. I don't want to put it there. Instantiate it. That's not what I wanted. All right, now we have our navx. Our subsystem home method is happy, right? We can zero the yaw and we can reset the encoders. Our onFirstStart method is happy. So let's take a look at these two methods, the setDriveOpenLoop and the setDriveVelocity. Well, as the methods imply, one method will set the drive output using open loop control, like for teleop control with a joystick, to that value. That's the setDriveOpenLoop. The setDriveVelocity will use the velocity control mode on the talons to request a velocity output from each side of the talon. So let's take a look at those methods. So this setDriveOpenLoop method is pretty simple, right? We have this class called driveMotorValues. Well, the driveMotorValues is really just a container class that we've used as a convenience that can hold and a left and a right drive value. And we'd use this simply to be able to pass values to the left and the right drive at the same time. That way we only have to pass one variable. So let's import that class into our utilities folder. Let's import, okay. Okay, so now we have this drive control state and a control mode. Well, let's look at drive control state. It's just an enum. It describes the modes that our drive base can have, right? Open loop, position, velocity, path following, turn to heading, and test. We're going to be implementing the open loop and the path following modes. But let's grab the whole enum. Okay, so now we have a drive control state. We import that, and now we have a control mode. Well, control mode is just in the Phoenix library, right? So we can import that from Cross-the-Road Electronics. That's just the mode that tells the Talon what it should be running. Now we have our own set control mode method, and let's take a look at that. Basically, what the set control mode method does is it provides differential updates to the control mode. Meaning, if the control mode is not equal, if the requested control mode is not equal to the control mode that we're in, then change it. Otherwise, don't do anything. That way we can call that method again and again and again without taking up cycles of actually changing the mode. We only change it if it's a different mode from what we are, right? But in order to do that, we need an instance variable that holds our current mode. And it's around here somewhere. Okay. Now, this mutex is a little bit difficult concept to explain. Basically, it's a way of synchronizing things across threads. When you do cross-threading interaction, when you have multiple different threads that are trying to interact with the same variable, when you perform writes to, or modifications to that variable in any way, you need a way to tell any other thread that may look at it that you're busy updating it, so wait until I'm done updating it before you do anything else with it. And the way to do that is to use a mutex every time you access that variable. And then you lock it before you access the variable, then you access the variable, and then you unlock it. Now, very bad things can happen if you forget to unlock it, like your code will just deadlock, and you really won't have any error messages. It'll just be hanging forever waiting for you to unlock your mutex, which it never does, right? So you have to be very careful to make sure that you always unlock your mutex when you're done with it. The recommended way of doing this is using a finally block and actually putting the unlock in the finally block. That way, even if an exception is thrown, you will always run the unlock on the mutex. But if an exception is thrown there, you got bigger problems. So we're just going to leave it the way it was. But yeah, if you're writing this code, I would encourage you to use mutexes with the finally block. So in Java, the mutex is really a C idea. In Java, a mutex is considered something called a reentrant lock, and it's a built-in class. So we just want to grab our subsystem mutex reentrant lock. Okay. Great, so now our set control mode is all set. Let's look at what else we need. Well, we need our set breakmode method. So what that does is just update the breakmode on all of the talons at once. Similarly to the control mode function, it only does an update if the request is different than what we were before. So let's bring over an instance variable to help store. My leg's falling asleep here. Okay. Let's bring over our instance variable to store the break mode previous value. Now, an important thing to note with both the break mode previous value and the control mode value is that we really need to instantiate them first. Like, we can't just assume that calling it later is going to provide an update if we don't have something set to begin with. So in the constructor, I like to initialize the previous break mode value to false and then call set break mode true to force an update. And I'll also initialize the control mode variable to path following. And the reason that I initialize the control mode variable to path following is because in the start of the match, we start an autonomous. Okay, we won't be doing turn to heading, so we can get rid of that. And we don't need the tipping stuff because it doesn't work. So what's left now? Well, we need this set drive velocity, and we need the path follower itself. So let's get the set drive velocity. So here, you can see that we have a couple methods for this. We have an overload method, because there are occasional times when we'd want to call the set drive velocity without forcing a mode change, because the path following implementation uses the set drive velocity method, but the mode for path following is path following. So if we called set drive velocity forcing a mode change, we're going to be in path following mode, and then as soon as we call set velocity, then we're in velocity control mode, which is not path following mode. But if we call this method and say don't auto change mode the velocity, just update the velocity, then we're okay, because we don't change modes. We're still in path following mode. So now we enter a little bit of what I was talking about before regarding unit conversions, because we need to convert our velocity output to native units. So we have a wrapper class for that. Called util. And util is part of the trajectory following motion library that we've already imported. So we can just import this class. This neutral mode is part of the Phoenix library. We can just import that. And this is just for gain scheduling, which we did not do. So we'll take that out, right? We don't need to choose a slot. That's part of our wrapper, is choosing a slot of PID gains in case we want to change them on the fly. But we really don't need to do that. We're not shifting. That would be used if you were shifting between low and high gears. We only have one gear right now, so we're going to tune that. Okay, so couple things here. Right, we want to import the path follower, and then we need this update path follower method. So let's look at what mPath follower is and drag that instance data over. Okay, so let's grab these two here, current path and mPath follower. And those are just the objects that are part of our trajectory following motion library that we've already imported. Okay, and now we want our update path follower method. Okay. So these are just more things we can import. We don't need the console reporter. That's just error reporting. Okay, so there's this method, update path velocity set point. Let's grab that. Again, we don't need to do gain scheduling, so we'll take those out. Now we have this mRobot state. What is the robot state? Well, it's another class we can import. Now we need a couple constants. So for right now, I'm just going to drag over these control loop gains. And then we'll go over tuning them after. But these are gains that we've tuned from testing the robot and using our PID tuner and doing a calibration for a velocity control loop like we talked about with the manually adjusting the F term. Now, there's this high gear max set point that we want to look at, which is just basically like a maximum allowed output of our velocity that we have here, and they use that as a scaling factor for their output. Now we need this inches per second to RPM conversion. And of course the inverse after. We're going to need inches to rotations. Now let's grab the methods to grab our distances, our angle, and our velocity. So now we need another method, rotations to inches, right? And then RPM to inches per second. So the nice thing about this is that most of the math has been done for you regarding unit conversions. You just have to be careful with it because it does get confusing and there are a lot of different units going on. So what are you still complaining about? Override. Subsystem home. So we can't override a subsystem home if we don't have a base class to override from. Now, at the top of our drivebase subsystem, you can see that we implement a few interfaces here that make our drivebase subsystem allowed to be used for other things. So we have a critical system status interface that allows us to monitor the validity of the encoder signals. That way we know if we ever have an failure or an encoder failure or a cut wire. We have a diagnosable subsystem class interface that allows us to perform a test mode on all of the characteristics of the drivetrain. Compare current draw, speed, things like that. And then we have an interface called Reportable that allows us to generate log data and output that to our dashboard. But the interface that we're interested in right now is the custom subsystem. And it's important to note that the WPI library implements a subsystem. They have a subsystem interface. Don't use it. It doesn't do the same things. So let's bring over this custom subsystem. And in our drivebase subsystem, we're going to implement custom subsystem. So we must implement all of the methods that it contains, which we don't. So let's implement the methods init and register enabled loops. So inside of init is actually where we do all of our updates for setting our sensor phase and our brake mode, I believe. So we'll do the instantiations in our constructor, and inside of our init, we'll do our actual sets. Now, what else do we want? Well, for the talons, you should explicitly select your feedback sensor, right? And we're choosing the magnetic cross-throat electronics encoder. You should also select the velocity measurement period, which is one of the features of how the Talon SRX measures the velocity to use in its control loop. And you also should select a measurement window. And I think the window is the number of samples it stores for using its calculated average. Then you can set the gains and the motion magic parameters if you're using motion magic. But for our example with path following, we won't be using motion magic. We'll just be using the velocity control mode. Okay. So let's bring this stuff over, and I'll talk a little bit about how it works. So these are all things that are part of the Phoenix library. And these are constants that we have. What is happening here? So because we're not shifting, we'll just assign the same gains to both slots for safety. And all this method is a helper method that we've created, so we don't have to type out the entire config KP, config KI, config KD that the Talon library uses. We just put it all into one method so that we could save time. So let's bring over the Talon helper from the drivers into the drivers folder. Okay. Let's see what it doesn't like. Probably the console reporter. Okay, get rid of that. We don't need any reporting. All right, let's import it. Awesome. So make sure we set the gains on both sides, right? We want to set the gains on the left and the right, and we'll use slots 0 and 1 just so that everything has the same gains so we don't get confused between gain scheduling slots in the Talons. Now these are the gains that we have input into our constants file. And the last thing that we're missing here is the cruise velocity parameters for motion magic, but we don't need them because we're not going to be using motion magic, so we can just get rid of them. Now, we have to instantiate a couple things in the robot class so that things will actually work. So let's go back to robot. I don't think this is the right project. We're going to want our drivebase subsystem and our robot state estimator. So what we do is we build an array list of every subsystem that we want to implement. That way, we can instantiate everything with a for loop and just say, for every subsystem in here, run a init, and then for every subsystem in here, register its loop in the looper. But because we only have one subsystem, we won't do that. We'll just take this and create it. So the first thing we want to do is create our looper and our controllers. We don't really need the controllers, but we want to spawn that as soon as possible so that it can start setting up the talent objects. Bring over the looper. Now we have to bring over the robot state estimator and register it as a loop. Did I already bring that over? I did. Awesome. So now the robot state estimator is registered as a loop. But remember, our robot state estimator uses the drivetrain. So in theory, we should instantiate the drivetrain first before declaring it. But because we've done everything as singletons, even if we haven't created the drivebase subsystem already, when this method here is called for getInstance, the drivebase will automatically be instantiated by the robot state estimator, even though we haven't called it in robot yet. But I like to call it before robot, before the state estimator. Now, we have to register. We have to register the drivebase subsystem in the looper. And the way we do that is a little different, right? We pass it the looper and it registers itself. Okay. Now, that should be everything that we need to do our path following implementation. So let's take a look at now the autonomous section, because so far all we've done is we've enabled the robot to be able to follow paths. We haven't made any paths. We haven't made any autonomous modes. We've just put in the framework that says the robot can follow such path. But we still have to make those. So in autonomous, the very first thing that we do is start the looper, right? We want to make, like, we have all the things that we just registered to be able to use, we now need to call start, otherwise they won't run periodically. When we're in disabled, we want to call an exit auto method, because one of the biggest problems that can occur is that autonomous ends and your robot is stuck in some kind of path following mode, and then your teleop drivers can't control it, and then you sit there and do nothing for the entire match because your robot is still trying to do something that it can't do. So we force the robot to exit the autonomous mode, and we force the robot into open loop control so that no matter what, once autonomous ends, the drivers regain operation using the joystick. Right, so in disabled, we will call the exit auto method, we will call the looper stop method, and we'll also wait until we're not disabled. So this other method here that we've used is a thread rate control. It's just a utility to help with loop timing so that you don't have to do the try catch every time, right? The thread rate control basically is just a wrapper that does thread rate control. So let's import that into the utilities just to help us a little bit so we don't have to call try catch all the time. Let's take a look at it. So besides having more error reporting than it really needs, it's a pretty simple class. All it does is attempt to target your target loop rate by estimating the amount of time that it took from the last time it was called to the next time it's called. So it calculates a delta t, and then if you're within your tolerance of, if your loop only took 13 milliseconds to estimate and you were trying to target 20 milliseconds, it will sleep for those additional 7 seconds. But if your loop took 21 milliseconds to execute, it'll just continue on, right? It won't sleep for any period of time if it's not required. It will try to target as best as possible the loop rate that you set. So let's bring over our thread rate control. Okay. So now we need to exit auto. So the file reporter we don't need, the console reporter we don't need. Now we have this auto mode executor. That's going to be the thing that actually runs our autonomous mode. So let's bring that over. Okay, we can't import this because we don't have it yet. So let's bring over another folder. Let's figure out where it is. Well, the auto mode executor is underneath the autonomous framework folder. We can see here from the import statement that we need to bring over the autonomous framework. Inside the framework, there are paths, or inside the autonomous folder, there's a framework, modes, and paths. Inside the framework are the base classes that we need to be able to do what we want to do. Whereas inside the modes, these are the actual autonomous modes that we are running. And then inside the paths, those are the paths that our modes follow to accomplish what they want. So let's just bring over our entire autonomous folder into robot. Now, I'm going to get rid of all of the things inside the modes folder for now. It's not really a delete, is there? You can't get rid of them. All right, so we'll just go into file system and do it. And again, we'll do the same thing with our paths. Okay, so inside now auto mode base, it says we need an action. Well, what's an action? An action is inside of the actions framework. So let's go look at what we have for actions. Okay, actions framework. Pretty straightforward. Let's copy the actions folder over. Now, in our demo program, we don't have a cube handler, right? That's the ARM thing. So we're not going to be able to really do anything with that. So let's get rid of these. Let's see what we got. No, we got action here, right? So that satisfies that. And then this is just error reporting, again, which we don't need. Okay, so the auto mode base is happy. Auto mode executor, let's import it now that we have it. Everything looks good. Oh, looks like we need a set gyro angle on our drive base as well. So let's add that. Okay, perfect. We don't want error reporting. Now, there are two methods that we need for our drive base to request the path that we want to follow, and then to check if we're done with the path. All right, don't worry about this one. This entire thing can go away. We don't ever shift, so we don't need the shift action. We don't ever turn to heading. So the only thing that I want to do is I want to make sure that our framework compiles fully. And in order to do that, the only thing I'm going to do, but probably at this point I could have just brought over the error reporting. It would have been faster. We don't have an elevator in our example. Okay. And then we have this has passed marker method. So the things that we're missing are is done with path to check if our robot has successfully executed the trajectory, to set want drive path, meaning this is the path that we want to follow, and then have we passed a path marker. So let's bring those methods over. Okay, now we want is done with path. And now the drive markers are markers that you can place in the path that say when you've passed this point in our path, do a certain action, right? We can raise the elevator, move the arm, do whatever we want. There was a bug in the code from the Cheesy Poofs in 2017 that occasionally a marker would be missed. And the robot would hang thinking that it had never passed that marker. And I'm not sure if this version has that bug patched, but we found it at IRI this year. And it caused us some trouble along the way. So it is a caveat to be aware of. So let's also copy this force done with path to force quit the path following mode, and also has passed marker. And the bug ended up being like this value here had to be changed to false or something. It's just like this code is non-stock here. We return. There were occasionally the bug would happen because the path follower entered a null state, but the path marker would never have been passed. So to fix it, we've just checked that if the path follower is not null, check if itself is finished and or has passed the marker, meaning that if the path has completed, we've obviously passed the marker. And then if it is null, we're done with the path anyway, so just return true. Okay, so let's see if that builds. Does not build. What did we miss? Okay. So when we copied this stuff over, we were really lazy and did not remove any of the vision tracking from the cheesy poofs tracking the boilers in their thing. So we still need to put the boiler radius in our constants, which personally I'm fine with. We just have a little section at the bottom of a whole bunch of unused stuff that just helps us compile. Let's see what else we missed. Crash tracking runnable, of course, error reporting. It's getting us again. And we built. So not too bad. So let's close everything other than what we need here. And now let's see what we can do. So the interface to generate paths for this, we've updated from what the cheesy poofs had. For whatever reason, when the cheesy poofs make their path following generator web page, they never put a click interface on it where you can just click where you want the robot to go. And it infuriates me to no end because I have to sit there and type in the values of where I want the robot to be. So every time they come out with an interface, the first thing I do is add an interface that allows you to click on the screen for where you want the robot to go. So let's just say, because we don't have a real field here, let's just start with the robot driving in a straight line, right? So we'll create this, click this. I've extended the interface here a little bit to allow changing the start point just by clicking a button so that we have 3 different starting positions that we can start on the field. You can download files, import files, display code, copy to the clipboard. We'll just start with displaying the code. And what this interface does is this generates a path, right? And the path is something that we can follow. So first, let's name it. We'll call this straight path. You can go in the JavaScript file and change the header to match your team number too if you have to do any of the package statement changes. So let's make a new class. We'll call it straight path. We don't need the path adapter, right? We didn't do path adapting. So the values that are here, right, are x, y. It's a coordinate plane. So our x and our y. The radius is a value that changes the curvature at a point, right? So it's an estimation. you have to be careful with using the radius, because if you put a radius that's too big for a bend, you can get things that happen like that. And that's horrible because the path is all over the place. Like the robot doesn't know which way to go, right? So that radius is just way too big. But if we put a smaller radius, you want to be able to see the two endpoints. You don't want to have what looks like lines going in other directions because the robot will try to go in those other directions and it's not good. Similarly, you can change the speed of the points. But again, you got to be careful with this, right? Because inside of our constants file, we just copied over a few of these values without really talking about them. But inside here, we have like path following max velocity, max acceleration, and we also have here K-drive high gear max set point, right? Which really I think should be the max velocity over here, which is the same thing. But you don't want to exceed those. And you also want to make sure that the numbers in your constants file are attainable. Because if they're not, sometimes the robot will just spin in circles. So now, to run this, we're going to need to build a mode that calls our path, right? So we have all this empty space inside Autonomous that we haven't done anything yet. Let's go over and pull out the Autonomous code. We'll just do a straight copy-paste. Now, this stuff is selection stuff based on the game-specific data, right? We don't really need any of this because we're just doing a little testing of the mode, right? You can switch the mode however you want. Let's import our auto mode base. And this is where we actually call our mode to start. So now we have to change this so that it's not null and an actual mode. So let's go grab a mode. We'll just grab the most basic mode we can find. So we need to instantiate our path. And there are a few things that have to happen when we create a mode. The very first thing we need to do is call the action reset pose from path action. Now what that does is that goes into our robot state estimator and resets the estimated position to the expected starting position of the path that we generated, right? And we can see that here, start pose. When we call reset pose from path action, that's the absolute starting position that we're assuming our robot starts from, and that's basically what zeroes our odometer. Now, we have to run a new drive path action with our path. And that's going to be the action that actually follows the path. And then we run an action to wait for 15 seconds, which is the entirety of the autonomous period. Okay? So because of the way the looper is structured, it's threaded. Everything will handle itself. Everything should handle itself. Okay. So instead of where we have null, let's create a new basic mode. And then we start it. So now, let's just make sure that this builds again. No errors. Now we can deploy it to the robot and see what happens. All right, before I deploy the code to the robot, I am going to rehome the elevator. I had to think about that one. Just because I don't want it up where it can be damaged while we're doing stuff. Okay. But of course, we can't actually do that because we never disabled the tuning PID mode in our old code. So let's do that real quick. What? I really don't know why this is deciding to be a problem right now, considering we did it before. However, that's okay. So let's, a little nervous, let's run our autonomous mode and see if it drives forward like we expect. There's no movement. None whatsoever. What's that?
Better than too much.
Better than too much movement. I don't know about that. I would have settled for circles. Ugh. So now we're going to go on a troubleshooting rampage and figure out what we missed. Yes, we put in a new basic mode that should run the new drive path action straight path. Straight path is right here. Of course, when we implemented all of this, we took out all of the debugging statements, so we don't know what's happening. Never started the drive base because we never put anything in our registered enabled loops function. That's a pretty big problem. But hopefully, that's our biggest problem. If that's our biggest problem, we can live with that. So we're just missing our looper.register. Let's try that. All right. Those are the circles. We were looking for them. So the reason that happened is because, remember when I was saying that we use for loops to run our init methods? We didn't put the for loops in. I forgot to call init in our robot. So let's just do that. And I will deploy while I reset this. Deploy again for safety. You can never over deploy. Okay. So let's give it one more try. So that executed our path pretty well. All right. Now that we know we're not going to die when we hit enable, let's do some more fun things. Okay, so now what I'm going to try and make this do is come up, turn right, and then come up again, right? We'll do an S-curve. So let's go into our web interface here. We're going to modify the starting position a little bit because that was the wrong one. So we said we want to come out, turn right, and come forward. But we should come out a little bit before we turn right. So we'll put a point here, a point here, and a point here. Looks like a reasonable path that we should be able to execute here, right? So let's generate it and call it sample path. And all I'm going to do is in the basic mode, change where I created the straight path to the sample path. Okay. So now let's enable it. Right? Followed our path pretty well. So now, the next logical step would be, how do we implement more than one path, right? Because if we're trying to get somewhere to the scale, we're going to execute a path, get to the scale, do something, then go somewhere else, right? And when you guys hold this cord for me up while I push it back. Thank you. Okay. Am I on 4, Jim?
Yep. Good. There you go.
Okay, sorry about that, guys. So, let's make a little shorter path this time. So instead, what I'm going to do now is I'm going to use this as the sample path. And now I'm going to make a second path that starts from where I left off. And then I'm going to do that to drive forward and left. And we're going to call this second path. I have a copy to clipboard button. I don't know why I don't use it. Because it doesn't work. Well, it does. It just doesn't copy the whole thing. Okay. So now we can do another action, right? And the actions are what's going to be driving our robot to complete tasks, right? We can make actions to move the elevator. We can make actions to move the arm. We can make actions to move the climber, move the intake, do whatever we want. Everything is going to be an action. And then we're going to run the action in our autonomous mode that we've created. So the action that I'm going to make right now is a wait action, right? And it's just going to wait for 2 seconds. Then after that, then we're going to run action second path. But we have to create a new second path. So, I'm sorry, we can't do that. We have to create a new drive path action of a new second path. We got to do something. Okay, I missed a new. So that's how we now run an additional path. So let's see what that does. So I'm a little interested to see what it does for the first turn because those points are pretty tight. It might get all confused and go crazy, or it might work. So let's see what we got. So it's going to wait 2 seconds, and now it should drive forward again. So now we're able to chain additional paths back to back. So now we can tour the whole field. Next, I don't know if I'm going to demonstrate this, but I can if you want. There is the wait for path marker action, right? So if we use the wait for path marker action, we need to put path markers in. And in order to do that, we need to make longer paths, because as we've talked about before, they sometimes have issues, right? We've mitigated the issues. But for short paths, the path markers don't work too great if they complete near the end of the path. It's really kind of like a race condition. So if we have the robot come out, go to the right, drive forward, let's say at this point here, we want to place a marker. And we'll call this our marker. Now the markers, I believe, are case sensitive, so just pay attention to that. Okay. So now, in our mode, you can see an example of this. So we'll call this a wait for marker, or we'll just call this a new mode. Very simple. So we don't have an elevator that we can set. Remember that your first action in your mode always needs to be a reset pose from path action. Right, so let's import the rest of our stuff. Now we're going to leverage a couple of the classes in the framework called parallel and series action. So as it sounds, every action that you create inside of a parallel action will run side by side with each other. Everything you create inside of a series action will run one after another, and it will wait until each action completes before proceeding to the next. There were a couple updates that we provided to the parallel and series action framework compared to the original Cheesy Poofs 2017 code that could continually execute a specific method even if an action had already completed. But that was a minor bug. So I believe that this version has that patch now. And the important thing to note with the parallel and the series actions is that we can chain them together. Like we can put a series action inside of a parallel action, which is exactly what we're going to be doing here. So in order to do things in the middle of while we're driving, we can use a parallel action to run our drive path action, in addition to a series action. Now our series action is going to wait for the path marker action until we cross that path marker that we called our marker. Right? Now we can do our own action at the end. But we need to make an action, right? So let's make an action. So I don't want to start reprogramming all the other subsystems on the robot so that we can actually control the elevator and the arm. So we'll do one that's easy, hopefully. We'll do flash LEDs action. Right, so let's take a look at this. I really love copying and pasting code as templates, in case you haven't noticed. So in our isFinished, we'll just say return true, because we don't really expect our LED flash to take any time. There's no update conditions. When we're done, we don't need to do anything special. The only thing we want to do is that when we start, we need to actually make the LEDs flash. So our LED implementation is also polymorphic because it allows to be used for the RGB driver or the canifier, which is a CAN bus enabled LED driver. So we're going to bring over a couple drivers. Right, we'll bring over our LED driver canifier and our LED driver interface. And we need, in order to do that, we need the RGB color class that we've made to hold an RGB color into utilities. And we need a constant that's our default LED color. We'll just bring over all our colors. Okay, that makes this class happy. Now we need the LED controller. So our LED controller, I'll admit, is a little excessive. It implements a lot of different things that we can use for diagnostics. It indicates if the COM status, whether it's connected or not. It also has a Morse code translator that it can output messages in Morse code if you so choose. So let's bring in our LED controller. Of course, we need the Morse code translator. We'll bring that into our utilities. No error reporting. We need the thread priority, and we need a canifier. No error reporting. Okay. So let's bring over our constant thread priority. And inside controllers, We're going to need our canifier. Of course, we need the constant with our ID. And lastly, we need our method to get the canifier. Okay. This is unhappy because of the imports. Okay, and again here because of these imports. Okay, so now the LED controller should work. In the LED controller, well, first in our new mode, let's set our flash LEDs action. And inside that, we don't want to take anything in, right? If we really wanted to, maybe we could take in a color. Okay, now we need to create the LED controller subsystem. It is also a singleton. And I believe it also implements, does not implement register enabled loops. Okay, it's just its own thing. So all we have to do is call start. I think we can also choose a default state. Yeah, set requested state. So let's set our default state to blink. Okay. Let's actually set our default state to fixed on. Now in our action, where we start, let's do our LED controller get instance and set our requested state to blink. So now, when this action runs, it should blink. One more thing I'm going to do is bring in a joystick so that I can drive the robot back and I don't have to push it every time. But, of course, we don't have a regular joystick. We have a driver for the joystick. So let's bring in our joystick driver, which has a few extensions that make things nicer. Okay. Now, I am just going to enable teleop driving by doing a little math to make arcade drive. Why will you not let me import this? Oh, because it doesn't doesn't exist. So we don't need any elevator scaling here because we're not using it. Now we need quick maths class just for some simple conversions. We take the joystick values and we normalize them, accounting for a deadband inside. So that way that when the joystick is stationary, they're rarely perfectly at 0, and we just kind of neutralize the little bit of noise that comes from the joystick. So that should enable operator control at 20 milliseconds. And of course, don't forget, we want to exit auto and also start our looper. Okay, so if that worked, I should be able to enable it and drive it back. It might also go haywire. Okay. So, one thing that we forgot to do before I run autonomous was change the mode that we're using, right? We're using basic mode still, except now we want to use new mode. Okay, so now what should happen if it works is the robot will drive, and in the middle of the path, it'll flash the LEDs. The turns were a little sharp on our path. So those are the kinds of things that I'm talking about. If you put points very, very close together, sometimes it can't necessarily make the turns that it wants, and then it freaks out. So are there any questions about what we've done today? Is there anything else that you guys would like to see? Yes, no? Well, that's pretty much all I have for today. So if there's nothing else that you guys have, then you guys are free to go. Thank you very much.